Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing the part 4 of this video, or this series of videos for exam questions on acids and bases and buffers. Now I should make this more, I was thinking about renaming these sets of videos from exam questions more to exam styled questions, because it's not really technically exam questions, so they're exam styled questions. These aren't from the exam, but they're similar to what the exam would be like, so I'm going to probably change the titles to exam styled questions. But apart from that, this is going to be this question is slightly different, but it's more of a continuation of part 3, in terms of it's a similar mindset going into this question. If you watched the last video, so as if you haven't watched the last video and you're completely baffled on acids and buffer questions, I did an 8-mark question on there. I haven't really counted the amount of marks on this question, but I can always do it towards the end. As I said, I'm not doing this under timed conditions. I'll be doing that in another video when I go through all exam questions related to this unit of year 2 physical chemistry, and one of them will be acids and bases. I'm just explaining how to go about answering questions like this. So this is another buffer related question, and this isn't specifically buffers, but in a way it is sort of like a buffer, but it's measuring, being able to calculate the pH when adding a strong base to a weak acid. And there's a couple of assumptions I need to make through this. And again, if you don't know anything about this topic, I'd really suggest looking at my previous videos in relation to before the exam style questions, where I go through how to go about answers, how to go about understanding certain parts of acids and bases. But this is me explaining how to answer this particular question. So without further ado, I'm going to go straight into this. So question 9, calculate the pH of a solution formed after 25 centimeters cubed of 0.18 moles per dm cubed. Sodium hydroxide is added to 30 centimeters cubed of 0.3 moles per dm cubed methanoic acid, and the Ka is equal to 1.57 times 10 to the power minus 5. Okay, so the first thing I always do, and I'll show you why I always do it. I want to change it from this to this. I don't like using the fountain pen in this case. So HCOOH. Now, as I said in previous videos, why I like to write out the equation, or write out this equilibrium, it's not necessary. It doesn't give me the marks, but as you'll see later on with these questions, it allows me to go and make annotations to help me understand how to answer a question later on. If I need to make any assumptions, or if I need to understand something, writing out the equation is just good, because it only takes you like 10 seconds for me to do that, and I can annotate it later on, and it helps me with my calculation. You don't get any marks from this, but I really suggest just writing at the start of any of these questions. You may not have to use it, but just know that in case I need to go use it or need to think about what's going on, I have that there. So that's why I write down. I have that there. I also write down my equation, because I've got Ka in this equation, and I think I'm probably gonna have to use it at some point. So we know that this is the equation. This is the acid dissociation. This is an acid dissociation in itself, right? We know it's a weak acid, but it's an acid dissociation, and any dissociation is always your products over your concentration of your products over the concentration of your reactant. So multiply that here, and these are always going to be multiplied. There's no powers in this case, because there's no molars. There's no difference in my molar ratio. There's 1-to-1 molar ratio, so there's no need to introduce any different types of powers. So HCO minus times by H plus over HCOOH. Great. I have information here. So the first thing I'm going to look at, right, and even now, you're still thinking of what am I going to add now? The very, very first thing that I want everyone to do, whenever they answer any of these questions, right, always work out the moles. I think it's something I haven't mentioned in videos before, but it's like one of my teacher told me this, and this is like years ago, but I remember my teacher always told me is that if you're ever struggling on one of these big mark questions, right, if you're ever struggling on, by the way, if you don't want to hear me speak and you just want to go straight to the answers and all that, just go to the end and you'll have it there. But I'm going to try and explain going through this step by step, right? But my teacher always said to me, always, if you get any of these long-winded questions, right, and you have no idea what you need to do, you can always gain automatic easiest 2 marks of the entire exam. Just work out the moles. You always get marks for working out the moles. If you go to any mark scheme where they have the concentration and the volume in the question, there's a very, very good chance that they want you to work out the moles. and if you have no idea how, even if you have no idea how to answer the question, just work out the moles. If there's, and here I can see there's two opportunities for me to work out the moles for two different compounds, right? Just if you work out the moles, easy 2 marks, and that's it. Like, even if you don't do it, complete the rest of the question. So I advise that. So again, I'm still not entirely sure what I'm going to do here, right? But I know I need to work out the moles of sodium hydroxide. So moles of sodium hydroxide, right? Again, I will go and explain what's going on here. But I just wanted to say that we need to work out this, right? So 0.18, the moles is equal to concentration is equal to moles of volume. So moles is equal to concentration times the volume, right? So 0.18 multiplied by 0.025. I forgot to mention this is I should have done this as 25.0 centimeters cubed. I always forget to write 25.0 centimeters cubed and 30.0 centimeters cubed, because that's how they have it out in the. I could leave it as two significant figures. I'll probably change it later. Anyway, we'll see towards the end. And I get my calculator out, so that's 0.18. 0.18 multiplied by 0.025. That's going to be equal to 4.5 times 10 to the power minus 3. Moles. Moles of methanoic acid. That's 0.3 multiplied by 0.03. If you're wondering why 0.03, we're doing this in decimeters cubed. We always you measure the volume in decimeters cubed. So volume of, again, if you're actually, I don't want to write that there. I'll write it here. Volume of methanoic acid is 30 over 1,000, right? Or times 10 to the power minus 3. Now, I don't really see him giving a mark for working out the volume. That's why I just go to this, because I can clearly see here that 30 centimeters cubed is clearly 0.03 decimeters cubed, right? I can just see that. The reason why I just go and write that down, because they don't usually give you marks for working out the volume. They just kind of like expect you to know that to convert from centimeters cubed to decimeters cubed, it's just timesing it by 10 to the power minus 3, or dividing it by 1,000, right? But in case you don't understand, I'm just writing it down in case you didn't understand how I got 0.03. So 30 divided by 1,000 is just 0.03, and 25 divided by 1,000, right? So the volume of sodium hydroxide, 25 divided by 1,000, or times 10 to the power minus 3, 0.025. And I can just see that because I've done these types of questions many times. And I've already said in multiple one of my videos, and you guys are probably getting sick of me saying this. If you want to know how to answer, if you want to know a topic, you got to know how to answer exam questions perfectly. That's the only way you can really know a topic very well. But yeah, that's why I just know that off the top of my head. I don't need to use my calculator for this. I can clearly see that this is 9 times 10 to the power minus 3 moles. Okay, we're here now. This is something that you should be able to do without even understanding the question. This is just something you should always, when you're attacking these type of questions, I expect that you should be able to get to at least this point here, right? So now let's actually see what's going on here. How are we going to actually attack this question? All right, so we have a solution of methanoic acid, right? And we're trying to work out we're trying to calculate the pH of a solution formed after we add 25 centimeters cubed of 0.18 moles per dm cubed sodium hydroxide. So we've added that, right? And we're adding this solution, we're adding 25 centimeters cubed of 0.18 moles per dm cubed to a solution of 30 centimeters cubed of 0.3 moles per dm cubed methanoic acid. So this is the solution in our beaker, right? The methanoic acid here, the one that's highlighted in red. And we're adding this solution here that's highlighted in yellow, 25 centimeters cubed of that in that solution, right? We know that sodium hydroxide is a strong base, right? It fully dissociates hydroxide ions in solution. Therefore, we can assume that the concentration of hydroxide ions is the same as the concentration of the unionized sodium hydroxide, right? So it's one assume that that's one assumption that we know, right? So actually I wanna put this here. I wanna just drop this a little bit down, right? So we know that we can make the assumption that the concentration of hydroxide ions is the same as the concentration of sodium hydroxide because it's a strong base and it fully dissociates hydroxide ions. So and in case you know what I'm talking about here, it's this. Now we can also, because we know that, we can also make another assumption, right? If I write out this equation here, you'll see what I mean. This is actually a 1-to-1 molar ratio. So as well as sodium hydroxide, the concentration of sodium hydroxide being equal to the concentration of hydroxide ions because it's a strong base and it dissociates fully hydroxide ions in solution, it's a 1-to-1 molar ratio. So we can therefore assume that the moles of sodium hydroxide, because the concentration is the same, and it's a 1-to-1 molar ratio, we can also assume that the moles of sodium hydroxide is the same as the moles of hydroxide ions in our solution, right? So that's what we have in there. So we have an excess. We have in this case here, because we've just made this, so we can assume we have 4.5 times 10 to the power minus 3 moles of hydroxide ions in our solution. So what does this actually cause in our reaction here, right? What's actually happening is that in this solution here, and this is why I say it acts like a buffer in a way, because it's the same properties as a buffer, right? Where the hydroxide ions here would react with the H plus, or the H plus will react with the hydroxide ions, right? To try and neutralize it. That's what happens. And we already said here there's 4.5 times 10 to the power minus 3 moles of sodium hydroxide in the solution. Therefore, 4.5, we don't know the moles of H plus, but we know that 4.5 times 10 to the power of minus 3 moles of H plus is going to react with OH minus. That's what's happening. So therefore, there's going to be the moles of H plus is going to decrease by 4.5 times 10 to the power minus 3 moles to react to the hydroxide ions. What this means now is there's less moles in the product than there is in the reactants. This causes equilibrium to shift to the right, right? This causes equilibrium to shift to the right to replenish those moles of H plus in our solution here, right? And therefore the moles of, by doing this, but in order to do that, right, in order to replenish this H plus moles, right, equilibrium needs to shift to the right, which means that the moles of methanoic acid, well, there's going to be more dissociation of methanoic acid, right? But 4.5 times 10 to the power minus 3 moles, 4.5 times 10 to the power minus 3 moles of methanoic acid will dissociate to try and replenish that H plus moles. So the moles of methanoic acid will decrease by 4.5 times 10 to the power minus 3 moles. In doing so, because the equilibrium shifting to the right, that's what's causing that, right? So the moles of methanoic acid will decrease by 4.5 times 10 to the power minus 3 moles to produce more H plus to counter the decrease in H plus, if that makes any sense, right? I think maybe I kind of muddled that. Maybe you guys didn't understand what I mean here. This is this H plus moles is decreasing. To counter this, or to try and increase it again, equilibrium has to shift to the right. In doing so, methanoic acid is dissociating more by 4.5 times 10 to the power minus 3 moles, the exact same mole to then, remember it's a 1-to-1 molar ratio, right? This is also 1-to-1 molar ratio, so it's going to be the same number of moles, right? So to replenish 4.5 times 10 to the power minus 3 moles of H plus, 4.5 times 10 to the power minus 3 moles of methanoic acid will dissociate to replenish that. Hopefully that makes sense. I think that makes perfect sense, right? So that's what's happened. So here we don't know. Here we need to work out we now have that information, right? We know this is going to decrease by 4.5 times 10 to the power minus 3 moles. And I'll do my equilibrium moles here in a second, right? I will do the equilibrium moles because you know, guys probably already know that, right? But looking back at this Ka equation here, I want to turn our attention back to this Ka equation, right? We need to work out, we need to work out the H plus. We already have the Ka, right? We already have the Ka. We're going to be able to, we need to work out the A minus, which is the HCOO minus concentration, and the HA, the undissociated methanoic acid concentration, right? So we need to work out the methanoate ion concentration and the methanoic acid concentration. First, we need to work out the equilibrium moles. Now, we can do the equilibrium. I'm going to write out the equilibrium moles here. So equilibrium moles. Actually, I don't like the way I just wrote that. Can't write, can I? I honestly can't write nowadays, you know. I think I'm losing it. Yes, I'm losing it. As you can see, I'm just lost it. I've lost it. I think I've lost the plot nowadays. I can't even write. Anyway, enough of my poor handwriting. As you can see with the equilibrium moles here, right? So as I've already said where the original moles are. So I have to work out the equilibrium moles. So moles of methanoic acid is going to be, we already have it here, is 9 times 10 to the power minus 3. That's the original moles of methanoic acid in our solution, right? So, but we already said it's going to decrease by 4.5 times 10 to the power minus 3 moles for the reasons I've already said. So that's going to be 9 times 10 to the power of minus 3 minus 4.5 times 10 to the power of minus 3. And that's just going to be, that's literally half of that. So 4.5 times 10 to the power of minus 3 moles. Right, so the next one we're going to do is the methanoate, if there is the moles of methanoate ions. Now you probably think to yourself, well, how am I going to work out what the moles of we haven't got anything to go off here, because the hydroxide ion concentration isn't going to affect the necessarily the it doesn't help us in understanding how what the methanoate ion concentration is, right? So how are we going to work out? There's nothing here to tell us how to work it out, but there is. Now, in our previous video, I already explained how this, and I did that at the very start, right? I did it all the way up here. And I'm going to explain it here again because I'm going to assume that you haven't watched that video. And I really suggest that you do. But if you want to help you understand it, right? We already know what the concentration of HCl minus is because we've given us the sodium hydroxide concentration. Now, I said this before, right? We can assume that the concentration of sodium hydroxide is the same as our methanoate ion. Why? Because we have to remember this. There's not only one. When we add this, I already said this when I was talking about with titrations, right? Because in a way, this is kind of like a titration. Well, it's not kind of. It is a titration, really. In terms of the fact that we're mixing an acid with a base, of a certain volume and a certain concentration, and I said here, it causes. This is acting as a buffer. The reason why you see this, like, it doesn't go perfectly downwards, or doesn't have like a gradual decrease. It's a very sudden drop, right? So I'm a bit technical. It's a very sudden drop, more or less a very, very sudden drop. It spikes downwards, right? There's a reason for that. You can see that it stays constant here for a very, very long time. Why? Because there's another reaction here happening, and it's almost like a buffer. It's a buffer, really. It's not almost like a buffer. It is a buffer. There's another reaction happening here, preventing a massive decrease in pH until you reach a certain point where, and it's the same thing that applies to down here as well, right? Until a certain point where the H plus concentration is greater than the A minus concentration, or A minus concentration, or vice versa, right? What you need to remember is that when we add, this isn't as straightforward as just saying Is only sodium hydroxide here and only methanoic acid here? No. What you need to remember is that there's another reaction occurring here where when the methanoic acid reacts with the acid, it forms a salt. Remember what happens when you have a base and an acid? It's a neutralization reaction, right? So a base and an acid forms salt and water, right? So you're gonna have the salt and water. This is what's gonna happen here. All of the sodium hydroxide is gonna get. Remember, we have less moles. We have a lower volume of sodium hydroxide than methanoic acid, right? Therefore, all of the sodium hydroxide will react with an excess of our methanoic acid, and it'll form a salt and water. So we'll have HCOONA plus water, right? All of this is the limiting. The sodium hydroxide is considered the limiting factor because all of it gets used up, whereas the HCOO, the methanoic acid here is the one that's in excess. So therefore, we can assume the concentration of sodium hydroxide is the same as the concentration of our salt, right? But then how the salt isn't really related? How is the salt related to the A minus? Well, we know that I don't like to write salts like this. I like to write salts out like this. HC, I don't know, it's a little bit high up. I like to write them like this. HCOO minus Na plus, because salts fully dissociate in solution, right? The HCOO minus plus our Na plus. Salts fully dissociate in solution. That's why I don't like to write them out like this. It's a very weak ionic, call it ionic interaction, or not even an ionic bond, an ionic interaction. Where they'll stay like this, but in reality in solution, they fully dissociate into HCOO minus and Na plus. So, and because it fully dissociates, i.e. equilibrium is far to the right here, right? We said that with the first one, the concentration of sodium hydroxide is the same as the concentration of our salt, right? And our salt fully dissociates into this A minus here. Therefore, we can say this. We know that the concentration of sodium hydroxide is the same as the concentration of our salt. And we know the concentration of our salt is the same as the concentration of HCOO minus. Therefore, this is why we're able to make the assumption that the concentration of sodium hydroxide, yeah, right? Therefore, the concentration of sodium hydroxide, the dots here just read the mathematics. In maths, this is how we represent the word therefore. That's just what, if you know what that means, that's just what it means. Therefore, right? Therefore, because the sodium hydroxide concentration is the same as the concentration of sodium methanoate, and therefore that's the concentration is the same as the concentration of our methanoate ion, we can therefore make the assumption that the concentration of sodium hydroxide is the same as the concentration of our methanoate ion. And because this is a 1-to-1 molar ratio, look, 1-to-1 molar ratio here and a 1-to-1 molar ratio here, we can also assume that the moles of sodium hydroxide, right, are the same as the moles of our methanoate ion. And this is our equilibrium mole, right? So we already have our equilibrium moles of our methanoic acid and the equilibrium moles of our A minus. So moles of, again, you don't have to write all of this during your when you're answering this question. I'm just writing this down to help you explain. HCOO minus is equal to what was it that we had? We said it's 4.5 times 10 to the power of minus, 4.5 times 10 to the power of minus 3. So 4.5 times 10 to the power of minus 3 moles. There we have that. Great. So we already have our moles now, in our equilibrium moles in our solution, right? Now we need to work out the concentration. So we need to work out the total volume before we do that. So the total volume of our solution, we already said the one is 0.03 plus, so 30 plus 25, right? That's clearly just 40. Say 40, 55. I don't know why I said 40. I'm losing it. 55. So 0.03. I don't know why I said 40. use my mind, 0.03 plus 0.025, and that's equal to 0.055 decimeters cubed. Now, I'll go through the marking towards the end. I'll go through the marking at the very end. I'm not bothered to do that as I go through. Now we can just work out our concentration. The concentration of methanoic acid is equal to 4.5 times 10 to the power minus 3. So 4.5 times 10 to the power minus 3 over 0.055. 4.5 times 10 to the power minus 3 over 0.055. That's going to be equal to 8.18 times 10 to the power minus 2. 8.18 times 10 to the power minus 2 moles per dm cubed. And our moles of methanoic acid, also our methanoate ion, sorry, is equal to, is also in this case actually rather coincidentally 4.5 times 10 to the power minus 3. That's a terrible 3. Don't like what I wrote my 3 there. I act like people can make these changes on paper, but you can't. No need to calculate it again. That's 8.18 times 10 to the power minus 2 moles per dm cubed. We rearrange our equation because we rearrange this equation because that's what we're trying to do. We're trying to work out the H plus concentration, right? So the H plus concentration is equal to our Ka multiplied by our methanoic acid, or HA, over our methanoate ion. Now, I still write it out for the sake of showing the examiner that you understand what's going on, but mathematically, you technically, in this case here, because they're both the same thing, you have the exact same thing on your numerator and denominator, they just cancel each other out. But I would just write out just to show the exam, because it may be you may get a mark just for showing this, but I'd still write it out and then you can cancel them out later. But yeah, so what's our Ka? So they said our Ka in this example here is 1.57 times 10 to the power minus 5. So 1.57 times 10 to the power minus 5. I can just see that it's just that's 1.57 times 10 to the power minus 5 is just our H plus concentration in this case. But I will cancel them out. I will write it out, because I can just see that you don't have to write this out. But examiners can be very, very, very stingy sometimes. H plus concentration is just going to be equal to 1. So I want to have square brackets. It's not really important. I just want to have square brackets. I don't know why. Just my OCD right now. It doesn't make a difference. I just want to write it out. Something about it. Okay, 1.57 times 10 to the power minus 5 moles per dm cubed, because it is a concentration. Therefore, the pH, remember, is equal to minus log base 10, or you can use the capital L here to represent that. When your calculator, it should be a on your calculator, it should be a base 10. That's what we're using, base 10 of 1.57 times 10 to the power minus 5. And then that's it. And now pH now is minus log base 10 of 1.57 times 10 to the power minus 5 is 4.8. 4.80. I could just leave it as 4.8 because now looking back at it, the lowest number of significant figures in this question is 2. So I'd leave it as 4.8. Even though it's an accident for me to put 2 significant figures. looking at our question here, it's 4.8. So 4.8 is this. Does that make sense? It does make sense. It does make sense because remember, in this case, we have more moles of our acid than we, so we have a higher concentration of our, sorry, we have a higher volume of our acid. And actually, no, we do have higher moles of our acid as well. Our original moles of our acid is double the size of our moles of base. I know we have a strong base. We're introducing a strong base, but overall, there's more moles of acid than there is base. Even given the fact that it's a strong base and a weak acid, right? So, and as already explained, this is acting as a buffer for the reasons I explained in this area here, right? So overall, we still have more moles of acid than we do base in our solution. I mean, they kind of cancel each other out, right? But, well, 4.5 times 10 to the power minus 3 of it is going to become our salt. And the other 4.5 times 10 to the power minus 3 of it is just undissociated, or just methanoic acid, right? Some of it dissociates a little bit, really. But we have more moles of acid than we have base. So this is acting as a buffer in that case. So if basically this is meant to be one of those graphs where we have a weak acid, strong base. So this is, let's just say the 7 mark is here, right? So it's got a, right? This is what's happening here, where the pH would increase from where originally it was. However, it's going to be maintained at that because of this equilibrium. Because of this equilibrium here, that's what's causing our pH not to go extremely high immediately, because of this equilibrium shifting to replenish the H pluses that were lost due to them reacting with hydroxide ions that were added to our solution. Hopefully this video was helpful, and that's it.